Right, shall we make a start, ladies and gentlemen? From near the microphone. Yeah, no. Welcome to this Institute of Physics, it's just disappeared, but it is an Institute of Physics, University of Birmingham public physics lecture. I think this is the second one that we've done so far this year. Today's lecture is going to be by Dr Anjali Piette, who's from our exoplanets research group. And we're looking forward to a talk on what is the weather like on alien planets. So I'm certainly looking forward to that. There are a number of other talks coming up across the Midlands at Worcester and Kiel, as well as Birmingham. So if you're interested by tonight, just gone, but that will cycle round and we'll put it on at the end. There might be some other talks that you're interested in attending. But for now, shall we welcome our speaker for this evening with a round of applause, and then over to you.
Okay, that looks like it's working. Good evening, everyone. It's great to see so many of you here. Thank you for coming. As Dan said, my name is Anjali. I work on the atmospheres of planets orbiting stars other than our own, also known as exoplanets. And it's been a really exciting couple of years in this field. Some of you may have heard of a new telescope called the James Webb Space Telescope, which went up into space a couple of years ago. We've been getting a lot of new data from that telescope. It's been really fun to play with. And this evening, I want to share some of our initial results with you and show you how powerful the telescope is and what it's helping us to do. But before I dive into that, I'm going to start off with a little bit of introduction. So I always like to ground us a little bit in what we're familiar with our own solar system. So we know that orbiting our own star, there are 8 planets, including the Earth, of course, here. And in general, for a long time, these are the only planets that we knew about before we discovered exoplanets. And we see a few trends here. So for example, out of the 8 planets, the 4 inner planets are rocky. We have Mercury, Venus, the Earth, and Mars. And then the 4 outer planets are gas-rich. So we have the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. So you might think, just from looking at the solar system, okay, all my rocky planets should be close to the star, and all the giant gaseous planets should be further away. Done, easy, planets are solved. That's great. It's actually not that simple. We only really started to learn about that by looking at the planets orbiting other stars. So if you're lucky, you may have seen a night sky as lovely as this one, an image from Northumberland, where in the sky you can see hundreds, sometimes thousands of stars. And when you're looking at that many stars in the sky, what you're technically also seeing is hundreds or thousands of planets as well, although you can't make them out, obviously, because they're much smaller and fainter. So we think that around every star in the sky, on average, there's at least one exoplanet orbiting that star. And if we think about the many, hundreds of billions of stars in the Milky Way, that means 100 billion at least planets in our galaxy. So that's a lot of places where we can look for different types of planets, maybe even look for signs of life. And what I really love about exoplanets is how diverse they are. We kind of thought that we knew how diverse planets could be from the solar system, roughly like rocky or giant. But it turns out there's even more diversity when we look at exoplanets. So far, we know of almost 6,000 exoplanets. This number keeps going up. I keep having to update it on this slide. It may have gone up since I made this. And these planets span a really wide range of properties. So this is a really nice graphic representation of just 1,000 of the known exoplanets, all artists' impressions. You can see that on here we have some really little rocky planets, not too dissimilar from the Earth. But we also have really giant planets. So just for reference, Jupiter is this planet here. And it's not actually the biggest planet on there. It's the biggest planet in our solar system, but there are exoplanets that are way bigger and puffier, like these ones over here. Like another really interesting dimension in the exoplanet population is temperature. So we have a nice, comfortable, habitable temperature here on the Earth, but that is not the case for a lot of exoplanets. the range of exoplanets that we know spans from less than minus 175 degrees Celsius all the way to more than 2000 degrees Celsius. I'm going to be telling you a bit more about one of the really hot cases a little bit later on. So you can imagine that if these planets have such a wide range of temperatures, that's going to have a big impact on their climates as well, right? It's going to change what the chemical, molecules and chemical species are in their atmospheres, the clouds, the dynamics, the winds, and it's going to change a lot of the properties in these exoplanet atmospheres. So today, for our exoplanet weather forecast, I'm going to be telling you about two case studies, two planets that we've been studying with a space telescope. One of them is going to be a roasted giant planet. So this is a planet not too dissimilar from Jupiter in terms of its size, but it's much, much closer to its host star compared to Jupiter. So it's really, really hot, and that changes a lot of things. And then the second one that I'll talk about is a slightly smaller and cooler planet where we have tentatively detected some steam in its atmosphere, but also signs of clouds and hazes. But before I get on to these specific examples, I just want to take us back to the first discovery of exoplanets and what it really means to detect these exoplanets and look at their atmospheres. So just for a bit of context, some of you may know this already, but the first exoplanet that was discovered around a star like the Sun, it was discovered in 1995. Now, for some of you, that might seem like a long time ago, but for others of us in the room, that's within our lifetimes. Compared to a lot of the physics that you might learn at school, which were discovered in ancient times, or at least in the early 1900s, this is actually a really recent discovery. So the very first exoplanet to be discovered is called 51 Pegasi b. It's a giant planet, a little bit bigger than Jupiter, and it's in the constellation Pegasus, which is where the part of Pegasi in its name comes from. And we might ask, why did it take so long to find the first exoplanet? Why 1995, after so many people, so many civilizations have studied astronomy? And the reason for that is that it's really hard to do. So just to give some context, if we were to look at the closest exoplanet to us, it would look as big as a tennis ball would look if the tennis ball was on the moon. So down here, I'm showing the size of the Earth compared to the size of the moon. This is to scale with the distance between the Earth and the moon. Imagine putting a tennis ball on that moon and trying to see it from the Earth. That's really, really small. Some of you may have some really nice telescopes that you use to look at the moon. You can see the nice craters and everything. Even with that, you would really struggle to see a tennis ball, right? That's how big the closest exoplanet looks. And there are many planets much further away. So it's pretty difficult to detect these things. You need some good telescopes, good methods to do that. And that's only detecting the planet. But just before I move on to the atmospheres, some of you may know this already, but the methods that we use to detect the planet, because we can't see them directly, in most cases we can't take a photograph of the planet next to the star because the star is too bright and they're too close together. So you need to use indirect methods to detect these planets. And so one way we can do that is that if the planet passes in between us and the star, then when the planet is in front of the star, it's going to block a little bit of that star and make it look fainter. So before the planet passes in front of the star, we see the whole star is nice and bright. Then the planet passes in front of the star. The star looks a little bit dimmer because some of that light is blocked by the planet. And then once the planet gets out of the way again, we see the full brightness of the star. This is what we call a transit. And this transit will happen every time the planet orbits the star. It'll keep coming back once a year for that planet. So that's how we detect, or one of the ways we can detect exoplanets. But how do we observe their atmospheres? That's a whole other ballpark, because we're not only trying to detect a planet, we're trying to look at this really specific part of this small planet out there in the sky, really far away. So how can we do that? There are a couple of methods, and I'll let you in on a secret. Usually the method that I'm going to tell you about is a bit more hard to explain, so it doesn't get talked about as often. It's also a method that has become more important with recent telescopes. So other methods get talked about more, but this is my favorite, so I'm going to tell you about it today. So the crux of this method is that the heat of a planet makes it glow. So we all know that stars emit light, and we can see that in the sky, but planets also emit light, just less of it and a different color. They technically mostly emit in the infrared instead of visible light. So we can imagine that in a similar way to how things glow on the Earth as well. So if you've ever used or seen an infrared camera, you'll know that people glow in the infrared. We can't see it with our eyes, but with the infrared camera, you can see that glow. And then some other objects that are hotter than people will glow in visible light. So you might have seen some like hot irons that glow sort of red or yellow. And if you remember from Bunsen burners, the orange flame is hot, but the blue flame is even hotter. And the trend that we're seeing across this slide is that as you go to the right-hand side of the slide, it's a hotter temperature, and hotter temperatures emit light at shorter wavelengths or bluer colors. So things around the temperature of people emit more in the infrared. Things as hot as a Bunsen burner flame will glow a blue light. So our planets are also going to glow with light, often infrared or sometimes a little bit of visible light as well. And we can try to look for that glow. But the glow from a planet is much, much smaller than the radiation and the glow from the star. So how do we detect this really tiny signal? So the key here is that, again, we're going to look at what we call these transiting planets, or planets that happen to pass in between us and the star. And then at the other end of the orbit, if we follow my cursor, the planet was also going to pass behind the star. And that's what we're going to use to observe the glow of the planet when the planet passes behind the star. And just as a quick aside, most of the planets, the exoplanets that we have detected, tend to be very close to their host stars. That's what we call an observation bias. It's just easiest for us to detect those planets compared to planets that are further away. And because these planets are very close to their stars, we believe that many of them are tidally locked, which means that they show the same hemisphere towards the star. So it's a bit like how we see the same face of the moon all the time. The planet shows the same hemisphere to the star, which means that one hemisphere of the planet is a permanent day side. The other hemisphere of the planet is a permanent night side. So that's already a little bit different compared to the Earth and the planets in the solar system. So when this planet is passing behind the star, we're seeing its permanent day side just before it goes behind the star. And just at this moment, what we're seeing is the light from the star, but also the glow from the planet. So we get a little bit of extra light from the planet. Then when the planet passes behind the star, we can still see the star, but we can't see the planet anymore. And that causes a small dip in the brightness that we see because we're missing the glow from the planet. Then when the planet comes back around on the other side, once again, we see the light from the star plus the planet. And the brightness goes back up again. So basically, the size of this dip tells us how bright is the planet. If we have a really hot, bright planet, this will be a really big dip. If we have a colder, smaller planet, this will be a smaller dip. And it's difficult to detect this. This is a pretty small dip in our data, but with modern telescopes, we are able to detect that. So, as I just mentioned, the amount of glow tells us about how bright and how hot the planet is, because a hot planet will emit a lot of or more radiation. So we'll get a nice deep what we call a secondary eclipse, a deep dip. And if the planet is colder, it won't emit as much light, as much radiation, and we will get a smaller dip. And so we can use the size of that dip that we observe to sort of backtrack how hot is the day side of this planet. Now, it's not only that gives us information about this atmosphere. We can also tell what the atmosphere is made of. And we do that using color. So when we observe the star and the planet and observe this dip, we can do that at different colors. So if you imagine taking a telescope or a camera, you could put a filter on the front of that. You could put a red filter, and then everything would look red. You would only be sensitive to red light. Or you could put a blue filter on and only be sensitive to blue light. Now, by looking at different colors, it gives us information about the molecules in the atmosphere of the planet. The reason for that is that molecules happen to leave very distinctive fingerprints in the light that's passing through the atmosphere. So this is just a little cartoon of an exoplanet. The center of the planet, the core or the surface, is emitting this glow because it has this warmth to it. The Earth does this as well. So we have radiation in the infrared, usually, that is moving upwards and outwards of the planet towards us and our telescopes. And as the light passes through the atmosphere, that's shown by these orange arrows, that light, some of it will pass straight through, go straight to our telescope. Some of it will bump into molecules or atoms in the atmosphere. Now, these molecules and atoms are kind of picky. There are some wavelengths of light, some colors that they really like to absorb, and other colors of light that they're not interested in. So if it's a wavelength that the molecule is not interested in, it'll just go straight through the atmosphere. But if it's a wavelength that the molecule likes to absorb, then it'll get absorbed by that molecule. It will not continue to travel through the atmosphere. And that means that the light that reaches us has been modulated by all of these molecules absorbing some wavelengths, but not others. Now, this is something that, I've just shown the example of a planetary atmosphere, but this is something that happens in stars as well. And because stars, especially the sun, is nice and bright, we have some nice visuals to show that. So you might have seen before, if you take a prism like this and pass a ray of sunlight through it, you get your nice rainbow. If you make a really, really fine rainbow with some nice instrumentation, you see this image on the right. So this is a real spectrum from the sun. This is actually the light from the real sun that's been split up really finely into the rainbow. And what you can see is that it's not a nice, smooth rainbow, right? There are all these lines in the spectrum. And these lines are colors that have been absorbed by atoms, in this case, in the atmosphere of the sun, so in the outer gaseous regions of the sun. So some of them are labeled. So this thicker line here, this is dark because hydrogen atoms have absorbed this shade of red. So that shade of red got absorbed by the hydrogen and it never made it to our eyes or this telescope or this prism. Similarly, over here, there are two stripes here in a sort of greeny yellow kind of shade. Those colors are always absorbed by sodium atoms. So they are missing in our rainbow because the sodium atoms absorbed those lines. They gobbled them up. And so there are more than just those lines. You can see there are loads of them here. And we can backtrack which atoms are in the atmosphere of the sun by looking at which colors have been eaten up, if you like. We can tell that because in a laboratory, we can take hydrogen or sodium and test, okay, which wavelengths of light does it like to absorb? Okay, I know that hydrogen likes this shade of red, and that matches up with this shade of red, so I can figure out that this stripe here in my solar spectrum must be from hydrogen atoms. So we can do that as well with exoplanet atmospheres. The idea is that from the planet, or the core of the planet, initially there are many, many colors of light radiating out. Here I've shown them as red all the way to blue. And then if we have a molecule in the atmosphere, for example this one, that really likes to absorb yellow light, then with my telescope here, I can notice that, okay, I can see the red light, check. I can see the orange light, I can see the green, I can see the blue, but the yellow light is missing. Why is that? And then you might think, oh, well, I know that this molecule really likes to absorb yellow light. So if I'm not seeing the yellow light, then chances are that that molecule is there in the planet's atmosphere and it's absorbing that yellow light. So based on what I can see and which colors I can see, I can figure out, okay, I think that that molecule is in that planetary atmosphere absorbing the yellow light. Hence, I've detected that molecule in that planetary atmosphere. This is a technique that we call spectroscopy, and I'm going to be showing you some real data sets. This is obviously a cartoon, but I'll show you some real data and what that looks like in a second. But first, I want to show you the telescope that we use to make those measurements. You might have heard of the James Webb Space Telescope, and I like to show this picture. This is actually, it's not the real thing, it's a replica, but a full-size replica. And you can see all these people who are standing next to that replica. It kind of gives you a sense of scale for how big this telescope is. So a lot of us in the field are really excited when JWST, the James Webb Space Telescope, went into space. It was on Christmas Day, so we sort of got up early and tried to see the launch and make sure it was all okay. And it went really well. And it took a few months to get the telescope into position and to get everything switched on. But once the data started coming through, we got really busy trying to analyze it, looking at the different colors that it was looking at, seeing what's missing, which molecules can we detect in some of these planetary atmospheres. Which brings me to our two examples. So I'm going to start off with our roasted giant planet. This was one of the first planets which we looked at with the James Webb Space Telescope when it went up. And it's a planet that's a little bit bigger than Jupiter, but kind of a similar size. And we call it an ultra-hot Jupiter. It's probably quite obvious why, but essentially this ultra-hot Jupiter has a day-side temperature of about 2,700 degrees Celsius. So really, really hot. For comparison, Jupiter has a temperature of about minus 110 degrees Celsius. So it's quite a bit hotter. And this is a planet called WASP 18b. Sometimes the names of exoplanets can sound a bit strange. They're often named for the surveys that were used to discover the planet, or also the name of the star sometimes as well. So this planet was discovered by the WASP survey. Okay, so we observed WASP 18b using the method that I just described before. We're going to look at WASP 18b passing behind its host star. And when it does that, we notice that the glow of the planet goes missing, and then it comes back on the other side. So I'm going to do a really old-fashioned movie here. I'm just going to click through the observation. So just before the planet passed behind the star, we saw this level of brightness because we can see the star and the planet. Then the planet started to go behind the star, so we couldn't see half of the planet, and that made everything look a little bit dimmer because we're hiding part of the planet's glow. And then when the planet was fully hidden behind the star, that's when we saw the minimum brightness down here. So that gives us the size of our dip. It tells us the brightness of the day side of this planet. And what we did was we didn't just look at the size of that dip in one color, we did it in a whole range of colors. So every single one of these data points here, this is the real data from James Webb Space Telescope, and each data point corresponds to a different color, but not colors that we can see. They correspond to infrared wavelengths. And the y-axis on this figure is showing the depth of that dip, of that secondary eclipse. So how bright is the planet for each of these different colors? So you might see that down here, the planet is pretty bright, and then it looks a bit dimmer in these colors. And then it kind of looks brighter again, and then it's dimmer again, and then brighter again, and then dimmer again, and then brighter again. So it's kind of weird, isn't it? But actually, this sort of bumpy pattern is a fingerprint that we know is caused by water molecules. We know that because we've studied water molecules on the Earth. We can just put it in the lab, see which colors of light water molecules like to absorb. And this is a very distinctive pattern, these multiple bumps, very distinctive of water vapor. So as soon as we saw these multiple bumps, we knew that this was water vapor in this atmosphere, which is really exciting. You can even see it by eye. So that's already a really fun discovery that we made early on. But the other thing we can do is to look at the size of the bumps, because that also tells us how much water vapor is in this atmosphere. So the bigger the bump, the more water vapor you have in that atmosphere. But in this case, these bumps are relatively small compared to what we might have expected otherwise. So that means that in this atmosphere of this really ultra-hot Jupiter, we do detect water vapor or steam, but less than we kind of expected. And we realize that that's because this is such a hot atmosphere that the heat is ripping apart the water molecules in the atmosphere. So some of the water molecules do stay as entire molecules, but a lot of them actually get broken up into oxygen and hydrogen atoms that are floating around in the atmosphere. And that's why we're seeing less water vapor than you might have imagined, because of that extreme heat that's just breaking it up. So that was pretty cool. It's a very extreme environment. You wouldn't want to go visit. It's way too hot. Now, another interesting thing that we found for WASP-18b is its wind structure, or at least hints of what's going on. So for a lot of other hot Jupiters or ultra-hot Jupiters, because we have observed others, not just WASP-18b, we've noticed that a lot of them have east-west winds that carry energy from the day side to the night side, kind of around the equator, if you like. But when we looked at WASP-18b, we could see a sort of temperature map of the day side with our data, and we noticed that it didn't really look like that. Instead, it looks like the winds are radiating outwards from the center of the day side, and we actually have some north-south winds as well, or at least hints of that. So that was a little bit different to what we were expecting. And we're doing more work to follow that up. But one of the possible theories for that is that there could be magnetic fields on this planet which cause drag and prevent the winds going around the equator, and instead force the winds to go a little bit more north and south instead. So more to come on that, but those are just a few hints of what we can tell with some of this JWST data. Okay, so now let's move on to the second case study, which is a slightly smaller, cooler planet. I like to call this cloudy with a chance of steam. So this second planet is called GJ1214b. This is possibly a less imaginative name than the last one. And we call this type of planet a mini Neptune. That's because it's smaller than Neptune, basically, but it is still bigger than the Earth. So this is just showing you the size of GJ1214b compared to the Earth and Neptune. And the really interesting thing about mini Neptunes is that we don't know what they're made of. And yet, mini Neptunes are the most common type of exoplanet that we know about. More common than Earth-like planets, more common than giant planets like Jupiter. Mini Neptunes are the most common. Yet we don't have one in our solar system, and we don't know what they're made of. So personally, I really want to find out. Maybe you do too. There are a few options for what mini Neptunes could be made of. One is that you could have a kind of rocky core in the middle, something that looks a bit like the Earth or a scaled up version of the Earth, and then with a sort of puffy hydrogen-rich atmosphere around that rocky core. Another possibility is that mini Neptunes could be what we call water worlds that have really thick oceans covering the entire planet. You could still have a bit of a hydrogen atmosphere around the water, but that would be a very different interior composition compared to the rocky case. So we actually still don't know whether mini Neptunes are one scenario or the other. Both scenarios might exist out there. But going back to the example of GJ1214b, we know that this particular mini Neptune is enshrouded in clouds and hazes. So we actually already knew this from before JWST based on observations with other telescopes. And actually these clouds and hazes, it's really cool that we can detect it, but it's also a little bit annoying because it blocks our view of the atmosphere. For that ultra-hot Jupiter that we saw before, we could see those nice bumps, we detected the water vapor. With GJ1214b, the clouds actually get in the way and make it harder to detect different molecules in the atmosphere. But that was before GJ1214b. That was before JWST. So when JWST went into space, we used that to observe this planet, GJ1214b, again. And instead of just looking at when it passes behind the star, we were actually able to look at the planet all the way around the whole orbit. And that means that we can look at how much energy was glowing from the day side and the night side all the way around the orbit. So that's a lot of information and a really rich data set. And something that we found is that this planet, GJ1214b, is colder than we expected. We know that it receives a certain amount of energy from its host star, like we receive energy from the sun. But the energy that it's emitting and glowing is actually less than that. And what that tells us is that GJ1214b has clouds and hazes in the atmosphere. So hazes are a little bit like clouds, but more like a smog, if you imagine that in a city, little particles floating around in the atmosphere. And these hazes and clouds can be very reflective. And what's happening is the light from the star is reaching the planet, but then half of that light is actually being reflected straight back. And the other half is going into the planet and warming it up. So only 50% of the light from this planet's host star is making it in. For reference, on the Earth, about 70% of the Earth's radiation that reaches us comes into the atmosphere, and about 30% is reflected off into space. So this is a pretty shiny planet, effectively. It's reflecting a lot of that light. So, even though before, with previous telescopes, we weren't able to detect molecular fingerprints in the data, with JWST, we actually were able to do that, although tentatively. So this, again, is a plot a little bit like the one for the ultra-hot Jupiter, where we have data points for every different color here, again, infrared wavelengths. And the y-axis is what is the depth of that dip when the planet passes behind the star. So how bright is the planet at all these different wavelengths? And here it's not the multiple bumps that we saw before. It's just a little dip right here. It's pretty subtle. And this dip is pretty distinctive of water vapor again. But there's a bit of uncertainty here because there's another molecule that also has a fingerprint around here, and that is methane gas. So we think that there's a good chance that this is water vapor causing this dip, but it is also possible that there could be a bit of methane gas contributing to this particular fingerprint. So we're not 100% sure, but those are the two sort of best candidates to explain this. And we're really excited that we got some kind of information of the molecules that could be in this atmosphere, because it's a really, really challenging one to do. Okay, so that takes us back to the question, what are mini-Neptunes made of? And as we reach sort of the end of this talk, I want to tell you about an interesting other method that we can use to learn about these really exciting planets. So, okay, we have, let's say, a mini-Neptune. We want to know what's the middle of the planet made of. Is it rocky? Is it water-rich? But when we look at this planet, we see the atmosphere around the outside. We can't dig into it because it's really far away. So what can we do about that? Well, if we do just a thought experiment first, let's forget that this doesn't sound very realistic. What if I were to take this mini-Neptune and just take the atmosphere off? Shazam, there we go, no atmosphere. Oh, we can see straight into the core of the planet. That's cool. But it's still really far away, so it's just a little rock in space. I can't tell what it's made of. I can't go and dig up that surface. This isn't really useful to me. So what if I move this rock really close to a star so that it gets really hot and starts to evaporate the rock at the surface? Would that help? Yeah, that kind of helps, because now that this planet is super, super hot, it can be thousands and thousands of degrees Celsius. The rock, if it's rocky, can actually melt. Like in a volcano, you can have a lava pool on the day side of the planet, and the lava pool evaporates. So you can have rock chemical species which evaporate into the atmosphere of the planet. Now that I can work with, because we have methods to study the atmospheres of these planets. So even though I can't dig into the center of this planet, what I can do is, if it's hot enough and evaporating the surface into the atmosphere, then I can see that evaporated material. So that's a method that we are starting to use to try and find out what the surfaces and interiors of these planets are made of. And this is just an artist's impression of one of these lava worlds, as we call them, that we're looking at. There are several that are being targeted by the James Webb Space Telescope, and still tentative results for now, and many data sets being processed at the moment, but it's something that I'm really excited about in the near future, and it could help us to learn more about the composition of not just the atmospheres of exoplanets, but their surfaces and their interiors as well. So eventually, we're really building up this bigger sample of JWST data sets of different types of exoplanets. I've shown you an example of a giant planet and also a mini Neptune. There are smaller planets, rocky planets, that are also being observed now and that have been looked at. And as we get these data sets from different types of planets, we can kind of piece together this bigger picture of what's happening in the atmospheres of exoplanets. How do they look different from the solar system and from the Earth, and trying to get this global picture of how planets work and how the weather works on those planets, and ultimately to get a better understanding of planetary science as a whole. So I'm going to stop there to make sure we have time for questions, but thank you very much for listening.
Right, so thank you